Okay, so in this video, we are going to be talking about Dalton's law of partial pressure, and that's the last part of chapter 8 is section 8.8 and partial pressure. So according to Dalton's law, um, when you have a mixture of gases, the gases act as though they are singly occupying that space in which they are. So what I mean by that is you have the cylinder here of just helium gas, all right? The same size cylinder. Now this contains argon gas. So because there are less particles here, the helium gas has 2 atmosphere pressure that it's exerting, whereas the argon with more particles is exerting a pressure of 4 atmosphere. Now when you mix up the same 2 gases into maybe another cylinder of the same size, then what you see is that the total pressure is 6 atmosphere. That means each gas is acting as though it's occupying that space all by itself and exerting its own pressure. So the total pressure is the sum of the individual pressures of each of the component gases, all right? So that's what Dalton's law is. Dalton's law states that the total pressure, P total, PT, is equal to the pressure of first gas, the second gas, the third gas, depends on how many gases are there in the mixture, all right? So the sum of the partial pressures of each of the component gas, that equals the total pressure. Now here in this slide, we are going to be talking about 22.4 liters, which is molar volume, all right? Okay, so here you have a pictorial. They all look to be roughly the same size in terms of space. If this is a cylinder, for example. And then they all have 1 mole of gas. Now this is 1 mole of a pure gas, this is 1 mole of mixture, and this is 1 mole of mixture of 3 different gases, all right? But the total number of moles in each of these containers is 1 mole, all right? The atmospheric pressure is 1 atm, all right? So there is a pressure of 1 atm. It's 1 mole, and this acronym STP stands for standard temperature. So the temperature, a standard temperature is either 0 degrees centigrade or 273 K, all right? Standard pressure is 1 atmosphere or 760 millimeters of mercury. So at standard temperature and pressure, 1 mole of either a pure gas or a gas mixture will occupy this exact same volume of 22.4 liters. So the volume in each of these containers is 22.4 liters, all right? And this volume is referred to as the molar volume. All right, so the total atmospheric pressure, the 1 atm or 760 millimeters of mercury, is composed of the partial pressures of each of its component. 78% of that 760 millimeters comes from nitrogen, and that works out to be 594 millimeters of mercury. 21% contribution is from oxygen, and that works out to be 160 millimeters of mercury. Carbon dioxide and water vapor and all are the rest, and in very extremely small amounts, especially carbon dioxide, only 0.3 millimeters of mercury, all right? Now you compare it to the air in the lung, and you see that oxygen has come down, all right? From 160, it's come down to 100. Look at carbon dioxide. Carbon dioxide is really high, all right? So what happens is there is an imbalance between the carbon dioxide outside and the carbon dioxide inside the lungs. So in order to equalize that, the air that has a lot of carbon dioxide inside the lungs, the carbon dioxide diffuses out during expiration because you have to equalize the pressures in and inside and outside. All right. So expired air, out of that 40 millimeters of mercury, 28 of it comes out. All right. And 116 of that oxygen is coming out. However, more oxygen is getting in because it's getting carried through the blood to the cells. So when you're solving the Dalton law problem, make sure that you write down the equation, which is pretty simple. P total is equal to the sum of all the partial pressures of the component gases, and then either solve for the unknown, whether it's P total, or solving for the partial pressure of one of the component gases. So here you have an example. There is a scuba tank with a mixture of oxygen and helium. The oxygen pressure is 0.45 atmosphere and the helium is 855 millimeters of mercury. So the first thing is to convert that ATM into millimeters of mercury so that both are in the same unit. Once you do that, then you can add the pressure of oxygen and add it to the pressure of helium, and together that will be the P total. Okay, so 342 plus 855, and there was a missing x here, so the value comes out to be 1.20 times 10 power 3 millimeters of mercury. That's the total pressure. All right, another study check. It says that there's a mixture of helium and oxygen um, in a scuba diver's tank, and first convert the ATM into millimeters of mercury, because the oxygen partial pressure is being given in millimeters of mercury as being 1280 millimeters of mercury. All right, and they're asking you to find the partial pressure of helium. So convert the 8 ATM into millimeters of mercury, then subtract the 1280, the partial pressure of oxygen, and then you'll get the partial pressure of helium. Okay, so that comes out 8 ATM is 6080 millimeters of mercury. Subtract the 1280 from it, and you should get the partial pressure of helium, which is 4800, and that's answer C. All right, so how do we use this partial pressure when it comes to breathing and the supply of oxygen to the cells and the expelling of carbon dioxide? All right, if you look at the cells, the partial pressure of oxygen is very low. All right, partial pressure of carbon dioxide is very high as a result of respiration and all the metabolic processes. What will happen is the carbon dioxide, as a result of the metabolic processes, builds up in the cell. So it's really, really high. Now, the fresh air in the atmosphere, the pressure of oxygen is very high, partial pressure of carbon dioxide extremely low. All right, so that the air that is coming into the lungs has a high partial pressure of oxygen. All right, so that air that is coming through the oxygenated blood pumped through the heart, the partial pressure of oxygen is very high. So it will diffuse into the cells in order to kind of equalize, balance it out, all right, because it's low in the cells. Now, the oxygenated blood has some amount of carbon dioxide, about 40 millimeters of mercury, but however, it's higher in the cells. So then that will diffuse out into the blood. And then the deoxygenated blood is then again taken back to the lungs. All right. So now the partial pressure of carbon dioxide in coming diffusing out of the deoxygenated blood is quite high, whereas it's negligible outside in the atmosphere. So therefore, all of the carbon dioxide will diffuse out into the atmosphere during exhalation. Okay, so oxygen flows into the tissues and the cells because partial pressure of oxygen is much higher in the blood, the oxygenated blood. All right, carbon dioxide is flowing out because carbon dioxide partial pressure is much higher in the tissues and cells compared to the blood. Okay, so you can see the different values here. Oxygenated blood, pretty high in oxygen, and moderately high of carbon dioxide. The deoxygenated blood, a little bit higher of the carbon dioxide, less of the oxygen, and then in the tissues, it's oxygen is very much less, but carbon dioxide is quite high. Okay. So we already talked about this slide table, or this table rather, and we talked about inspired blood, inspired air, the air coming in, the lung air, and then the expired air. All right, in this study check, if I have a balloon with a volume of 4.5 liters and a pressure of 567 millimeters of mercury, what will the pressure be when the volume is 2.5 liters? You can use Boyle's law here, okay? You can assume that the temperature and moles are constant because they're not even being mentioned, all right? So, 567 P1 times V1, 4.5 liters, is equal to P2, you need to find that, and V2, which is 2.5, all right? So 567 times 4.5 divided by 2.5, and you should get the answer in millimeters of mercury. 15 mils of gas is collected at 25 degrees centigrade and 650 millimeters of mercury. What is the volume at STP? All right, so you can use the P1 V1 by T1 is equal to P2 V2 by T2, the combined gas law in formula for this particular problem, where the temperature is going to be 0 degrees centigrade or 273 K, and the pressure is going to be 1 atmosphere or 760 millimeters of mercury, and then you are finding out V2. 2.5 liters of a gas at 64 degrees centigrade and 700 millimeters of mercury is now subjected to a temperature of negative 33 degrees centigrade and a pressure of 900 millimeters of mercury. What is the new volume? And again, you're going to use the combined gas law formula here as well and solve for V2. An unknown gas having a mass of 5.5 grams is collected in a 4-liter glass bulb. It is found to have a pressure of 400 millimeters of mercury and a temperature of 27 degrees centigrade. How many moles of gas do you have? What is the molar mass of this gas? So first use the PV is equal to nRT, solve for n moles. Once you have the moles, divide the grams by moles because grams per mole is the molar mass. And that's the end of the chapter. I will have one more video to go over these study check problem, these last few study check problem, and as well as to list the homework problems that you need to do for this particular chapter.